Hello to everyone. In first part of this lecture, I will talk some general considerations on metals. Then I will connect these general facts with results from our studies on metal exposure in mother-infant cohorts from the continental and coastal parts of Croatia. And in the third part, I will talk something about benefits and potential risks of fish consumption, um, which is related to selenium and mercury levels in most commonly consumed fish species in Croatia. Well, what is essential element? Element is considered essential when insufficient ingestion results in harm or suboptimal function, and if supplementation with physiological levels of this specific element prevents or repairs the damage. People need more than 49 nutrients for optimal health, and among them 23 are elements which are involved in physiological and biochemical activities in the body. We categorized essential elements in macroelements, trace elements, and ultra trace elements. They're categorized by needs and our requirements. We need more than 100 milligrams per day macroelements, and these are sodium, magnesium, potassium, calcium. Among trace elements and ultra trace elements are those elements we needed less than 100 milligrams a day. On other side, we had the toxic elements. These are individual element or element compounds that negatively affect human health. Mineral elements contribute to the body structure, and we needed them to regulate body processes. They are important for regulation of acid-base balance, water balance. They are cofactors in for enzymatic activities in the body, like selenium, zinc, copper, and they have important role in protection against oxidative stress. Also, we need elements for energy, for physical activities, for health, immune system, blood cells functioning, and I would like to say that each element plays a unique role within the human body and should be present in its optimal concentrations. Humans and general population is exposed to different kinds of elements through food, water, air, cigarette smoke, cosmetics, but also due to specific diets regimes, like specific restrictive diets, parenteral nutrition, or chronic kidney dialysis. Routes of exposure and routes of elemental absorption is strictly connected to the source of exposure, and this is gastrointestinal route of absorption through gastrointestinal tract, respiratory tract, parenteral route, or dermal route. We have several factors that characterize benefits and toxic effects of elements. First is dose-response relationships. Each essential element can be also toxic if its intake is too high. Element deficiency are caused by inadequate intake or increased demands, impaired absorption, and the most common deficiency of elements are of iron, zinc, copper, and selenium. Also, elements interact within each other. Interactions among trace and toxic elements are also well known. For example, we had interactions between cadmium and essential elements iron, zinc, but also with essential element calcium and magnesium. If the intake is too high, they may reduce iron and zinc absorption. From animal studies, we know that high dietary selenium may also reduce toxic effects of mercury and cadmium. Bioavailability is also one of important factor to characterize nutritive and toxic effects of elements, as well as oxidation state. For example, for chromium, we know that chromium 6 is more toxic, and the chromium 3 is essential. For arsenic species, inorganic forms are more toxic than organic forms, like arsenobetaine. And according oxidation state, arsenic 3 are more toxic than arsenic 5. Women and young children are the most sensitive population groups to toxic metal exposure because in this period of life they had specific anatomical changes, especially women during periods of pregnancy, and requirements for nutrients. Increased demands for nutrients caused higher intestinal absorption, but not only of essential elements, but also of toxic elements. Food. Food is abundant in essential elements, but also we know that food can be a source of various toxicants, including toxic elements.
If you say that women are more,
Yes.
they can have more harm
Yes.
going to metal exposure, is it only when they are pregnant, or is there also
in this period of life they are more sensitive than in other periods in this reproduction period from
then we are as sensitive as men?
No, I would say that we are equal sensitive, but especially sensitive in those periods of lactation, pregnancy, and when we plan pregnancy, because we need to we need to be careful with food intake, and especially if we know that some special food is potential in toxic elements, like example fish, and I will talk about this later. Yes, food. In food, toxic metals like mercury, cadmium, and lead enters by through agricultural production, may enter in food by industrial or household processing, but also by migration for packaging during storage of final product. The most known food poisoning in past are occurred in Japan. Unfortunately, this was itai or ouch disease caused by chronic cadmium poisoning by ingestion of cadmium contaminated rice. Ouch disease was characterized by renal tubular dysfunction, severe osteomalacia, and anemia, and most of the victims were middle-aged women. Why? Because they were deficient in calcium due to lactation, multiple pregnancy, and postmenopausal calcium losses, but also due to low levels of iron. Minamata disease in Japan was caused by metal mercury poisoning due to consumption of contaminated fish and seafood. Scientific aspect of Minamata disease was the discovery that the metal mercury is transferred across the placenta to affect the development of unborn child, resulting in serious mental and physical problems in later life. In Iraq was also the largest mercury poisoning by inorganic mercury from mercurial fungicide. People eat a grain coated with those fungicides. And in Iraq, more than 6,000 individuals suffer from mercury intoxication, among which 500 died. So we need to monitor food contaminants, including toxic metals in food. What we do in our lab is exposure assessment to characterize risk. Finally, through several analytical methods, through monitoring programs, different or by total diet studies, we analyze sources of metal exposure. Primarily, this is food and water, but we also may, through this assessment, monitor soil, air, and other medias. We also do biomonitoring. Through biomonitoring, we analyze internal dose of toxic metal exposure. We analyze human biosamples, among which are common blood and hair. When we observed and when we have data about levels of toxic metals in food and we have data about internal dose of metal exposure, then we compare those dietary exposures with the human-based guidance levels and different metrics proposed by international agencies to propose some guidelines to protect consumers and protect general population from potential toxic intoxications. Well, cadmium. The main source of cadmium exposure in non-smokers is diet. And more than 80% of cadmium derives from cereals and vegetables and potatoes. We also know that higher intake of cadmium, dietary cadmium, had those populations with specific dietary habits, such as vegetarians and high consumers of shellfish and oysters. Also, from the epidemiological studies, we know that women have higher body burden of cadmium due to increased intestinal absorption of dietary cadmium at low mercury, at low iron stores, but also at low stores of calcium. In Asia, dietary cadmium exposure is higher than in Europe because of more polluting industries and a higher intake of rice and grains grown in contaminated area. In general population, with the diet, tobacco smoking is the common source of cadmium intake and exposure. Tobacco smoke is the mixture of various chemical substances. Among the most abundant metals in tobacco smoke are cadmium and lead. And we know that 10 to 20-fold higher is absorption rate of cadmium by inhalation than by ingestion. So tobacco smoking is more harmful source of cadmium than is diet. As well, we know that cadmium in placenta and is that higher accumulation rate of cadmium is in placenta, especially in smokers than in non-smokers. What are health effects of cadmium exposure? For chronic dietary exposure, main target organ for cadmium exposure is the kidney. Chronic dietary exposure leads to renal damage characterized by proximal tubular reabsorptive dysfunction. Also, on example of Ouch disease, we know that cadmium in chronic exposure may lead to bone resorption with higher, which may be intensified after menopause. Also, we know that cadmium acts as fetal teratogen, reproductive and developmental toxic, and endocrine disruptor. As I said previously, non-smokers had much lower cadmium levels than smokers. These are results of our study in mother-infant cohort in continental part of Croatia. In maternal blood and placenta and in maternal hair, smokers had approximately threefold higher concentrations of cadmium than non-smokers. We found no difference in cord blood between smokers and non-smokers because placenta is a very good barrier for cadmium, and cadmium, as I said, accumulated in placenta. Why we use placenta in our studies as a biosample? Because placenta is additional non-invasive bioindicator of toxic metal, especially of cadmium. We also use placenta for exposure assessment for mercury and lead. Placenta reflects past and recent exposures due to element redistribution during pregnancy. But due to accumulation of cadmium in placenta, cadmium in placenta interacts with essential elements and impair their transport to the fetus by competition for binding the same transporter proteins. From epidemiological studies, including our own, we know that maternal smoking during pregnancy may disrupt some placental functions. It may impair placental nutrient passage and antioxidant enzyme activity, especially of SOD and GPX, and affect steroid biosynthesis, which is occurred in placenta. These are results from our last cohort in Project Metal-Origins, which was conducted 5 years ago. Active smokers had higher activity of SOD in placenta, but in the same time, they had lower selenium in the cord serum, lower maternal serum, iron maternal serum, and lower placental iron. About effects of steroid biosynthesis, we found that active smokers had lower cord levels of progesterone and estradiol, which is a result of disrupted sex steroids in cord blood. Lead. Today, lead exposure in the general population decreased since 2004 because of the continued phase out of lead in gasoline and by other legislative control measures. Sources of lead exposure in general population is paint in homes, especially in those built before 1978, by water from lead pipes, soil, traditional medicines, foods, and cosmetics, but also jobs and hobbies which are connected with car industries, batteries. Most sensitive population are children, less than 6 years old, because I said they had increased absorption of all nutrients, including toxic metals, but also children in this age put their hands or other objects in the mouths. And we know that the dust may contain lead. What we do if our child has a high lead levels, we test our child for learning and developmental problems. We try to clean up all lead dust from our home, frequently wash hands and toys, and give child foods rich in calcium, iron, and vitamin C, because lead interacts with those elements, and those elements decreased then lead levels in our body. In our cohort, subjects recruited in 2007 and 2008, which was 10 years period between last cohort recruit in 2017. We can see a smaller drop in lead levels in maternal blood. In cord blood, lead levels were lower than reference levels for lead in cord blood, which is 12 milligram per liter. Cord blood lead was in the range of 51 to 76% of the mother's blood, which means that lead easily passes the placenta. The high drop was found in placenta tissue. Placental lead decreased during 10-year period about fourfold in our subjects. I would like to say something about mercury. And mercury is always connected with fish. When we talk about dietary exposure in general population, fish we know is a valuable dietary source of essential nutrients, especially of macroelements calcium, phosphorus, and trace elements iodine, selenium, but also iron, zinc, and copper. But as I said, fish is also a main dietary contributor to metal mercury exposure. Why? Because during biochemical cycling of mercury, mercury in marine organism biotransforms from inorganic form to organic metal mercury, which is very toxic and which is neurotoxicant. And in marine environment, mercury accumulated in organisms and biomagnificate through food chain, which means that those organisms which are on top levels of food chain had higher concentrations of metal mercury. Mercury enters in the human body by various routes and in different chemical forms, and different toxicokinetics in the body is related to these different chemical forms. In fish and seafood, mercury is presented mainly in form of metal mercury. Dental amalgams and some thermometers and fluorescent lamps are source of elementary mercury, and vaccines like thimerosal are source of ethyl mercury. As for all toxic elements, this is case and for mercury, that toxic effects depend on the form of mercury present at the time of exposure, duration, level, and route of exposure. Health effects of mercury exposure are related also to different chemical forms. So inorganic mercury leads to nephrotoxic effects, and organic mercury, for organic mercury target system is neurological system, nervous system. Organic forms of mercury easily passes the placenta, and mercury levels in cord blood may be from 20 to 65% higher than in maternal blood. The most common biomarkers of exposure to mercury are blood and hair. Blood reflects exposure of all forms of mercury, and normal levels for individuals with no consumption of fish are from 5 to 10 micrograms per liter. Hair addresses dietary exposure to metal mercury, and normal levels are from 1 to 2 micrograms per gram. And for those people who consume large amounts of fish, are more than 10 micrograms per gram. Urine is used for assessment of exposure in occupational for occupational exposure because it reflects exposure to elemental mercury. It's also good correlates with air pollution and derived from those mercury that accumulate in kidney cells. And in some epidemiological studies, researchers use placenta as non-invasive bioindicator. For mercury, in our research, we found very strong correlations between placental mercury and maternal blood and cord blood mercury. Here are presented levels of mercury in maternal hair in subjects from 17 European countries and in Croatia. In Croatia, we had, as I said, two cohorts, one from continental part, this was in Zagreb, and one in Zadar at coast. We can see that subjects from Zagreb, continental part in Croatia, had similar levels to most of European countries, which is 0.2 milligram per kilograms mercury in hair, and that this was pretty similar to average mercury value in hair in European mothers. But in Zadar, in coastal part, where we assume that subjects eat more fish, levels in their hair is similar to those of subjects in Belgium, in Denmark, Luxembourg, and Cyprus, when is higher intake of fish. Also, we found that subjects from coastal part had higher selenium levels and arsenic level in maternal blood in comparison to those from continental part, but those from continental part had higher levels of iron, zinc, and copper. These all results are connected with food intake because we know that iron, zinc, and copper are their source in our diet are red meat and cereals, and source of those metal exposure and intake are fish. These are presented results on levels of mercury and selenium in different biomatrices in two cohorts, continental and coastal area, and according in relation to fish consumption. These numbers from 0 to 3 reflects seafood consumption frequency. 0 is no consumption, and 3 is consumption more than twice per week. For mercury and for selenium, we found association between levels in biomatrices and fish consumption frequency. Higher fish intake was associated with higher mercury levels in all analyzed tissues, and this was approximately 4-fold higher in subjects who consumed fish more than twice a week than in those who consumed fish less than once a week or they do not consume fish. Levels of selenium also increased, but with fish consumption, but in a lesser extent than mercury. So we know that people from coastal Croatia had higher levels of mercury and selenium, but we don't know which fish contribute to this higher dietary exposure. Here are preferences from fish consumption in mothers from Zadar and Zagreb region. And from one of our questionnaire, we asked people which fish do they eat. We found that these species were sardine, hake, tuna, sea bream, sea bass, and some other marine fish species. So what we do next, what we done next is we analyzed metals, essential and toxic, in different marine and freshwater fish available in Croatian market. Samples were collected in collaboration with the Institute of Oceanography and Fisheries in Split, in collaboration with Croatian Institute of Public Health and Faculty of Food Technology and Biotechnology. We caught fish on 48 different locations in Adriatic Sea. We collected fish on main fish markets because we want to see a difference in metal concentrations between farmed and wild caught fish, about for species sea bream and gill and sea bass. And in restaurants, we collect samples of tuna fillets. How does it look like in the lab? Well, we first sampled our fish. Fish were first measured for total length and body weight, and then we dissected dorsal muscle tissue with ceramic knife. Muscle tissue was freeze-dried at minus 50 Celsius degrees for 72 hours to obtain the dry mass. Then muscle was homogenized and weight digested in microwave system. The last step was ICP-MS analysis. Before I present you our results, I would like to say some things about fish consumption in world and in Croatia. The most fish is consumed on Iceland and Portugal, Japan, Spain, and among those countries, from related to fish consumption, Croatia is in the middle on the global average of 20 kilograms of fish and fish products per capita. Most commonly consumed fish species are hake, then sardines. From freshwater fish, this is common carp, and tuna. And this fish we analyzed also in our studies, and these are results. Firstly, I show micro minerals. These are iron, zinc, copper, selenium, and mangan. Sardine had higher levels among those fish species of iron, zinc, and copper, while selenium levels did not differ among marine fish species and were lower in freshwater fish. We also analyzed tuna fillets and canned tuna, and you can see that selenium levels in those two products of tuna are pretty similar. But there is difference in mercury levels between these fish species. Hake, sardine, trout, and carp, including canned tuna, had mercury levels below 0.2 milligram per kilogram, which is twofold lower than the European regulatory limit for mercury in muscle tissue of fish. But tuna fillets have the highest level of mercury, which was above 0.5 milligram per kilogram. About arsenic, arsenic had higher level in hake. Hake is demersal fish species, and this kind of fish species had higher levels of arsenic. Luckily, arsenic contained in fish is mostly in form of organic species, which we know that cannot harm human health. They are untoxic, and in muscle tissue, arsen is present in form of arsenobetaine. We assess contribution of one fish serving of 150 grams in way of essential and toxic metals. And fish, we can say that is good source of copper, zinc, and iron and mangan, but is excellent source of selenium, especially marine fish. And by intake of one fish serving of marine fish, we can reach 76 to 200% of daily recommendation values for selenium. Here are results of mercury and selenium levels in muscle meat of 12 fish species from the eastern part of Adriatic Sea. From these 12 fishes, we categorized fish by trophic level in pelagic neretic species. These were European, this was sardine, anchovies, and chub, and Atlantic horse mackerel. Then we have bentopelagic species. These are brook and pickerels, and the demersal species, European hake, red mullet, shark, and common Pandora. In those fish species, the mercury levels range from 0.1 to 1 milligram per kilo in common Pandora. And the demersal fish species had 2 to 4-fold higher mercury than bentopelagic and pelagic neretic species. For selenium, there were lesser variations in levels between those fish species because selenium is essential element, and mercury is toxic element accumulate through food chain, and species like sharks and tunas and swordfish, which are on the top of food chain, had higher mercury levels, but also the demersal fish species, which are on the bottom of the sea, had also higher levels of mercury. This is case of red mullet and common Pandora. As we measure fish length, we can study then the relationship between mercury levels and fish length. And we found positive correlation with levels of mercury in the muscles and fish length for sea bass, for European hake, and for Atlantic horse mackerel. In hakes, there is change in diet after the first year of life, when it's 16 centimeters long. And prey changed from crustaceans to fish. So so mercury levels also decreased by fish size. The diet of specimens larger than 50 centimeters has characteristics of cannibalism, which means that hakes eat hakes too. For Atlantic horse mackerel is same story, which is in hake. They begins life as zooplanktivorous, but become piscivorous at adult lengths, and we found positive correlation as well with mercury levels and fish size. Selenium and mercury interacts, and due to these interactions, selenium and mercury form inactive forms, which are then excreted from the body. And when selenium to mercury molar ratio is higher than 1, this is good for consumers because selenium would interact with mercury. Mercury could be then excreted from organism, and we have enough selenium for as essential element for other functions. Selenium is needed in our body. From fish species we analyze in our lab, chub, mackerel, canned tuna, sardines have higher value of selenium mercury molar ratio, and those fish with higher mercury levels had lower selenium mercury molar ratio. From these fish, the lowest ratio had common Pandora, sportfish, and smooth-hound shark and tuna. Red mullet and sea bream had also pretty low selenium mercury molar ratio. What we found in our studies is that sea bream, which is among mostly consumed species in Croatia, especially those from wild caught in Adriatic Sea, had pretty higher levels of mercury, which are near the European regulatory limit for mercury. So to our assessment and evaluation of risk, we concluded that moderate intake of specific demersal species, like is common Pandora and wild gift-held sea bream, as well as high trophic level pelagic species that may have elevated mercury content, which is higher than 0.5 milligram per kilo, may increase the probability of health risk from mercury exposure in pregnant women and young children as most sensitive population groups for toxic metal exposure. Also, we propose that the need for continuous monitoring of fish species, especially of those two species, common Pandora and sea bream. For other fish species, including most commonly freshwater species that are common carp and trout, fish can be safely consumed from 2 to 4 servings per week, because those fish species had very low content of mercury, which was lower than 0.2 milligram per kilo. This is in line with EFSA recommendations, which stated that we need to consume fish at least 2 times per week to reach daily intake of omega-3 fatty acids, vitamin D, and other essential elements, including selenium. What we need to be cautious is about consumption of red mullet and sea bream. These fish should be consumed for 1 serving per week in combination with other species which are low in mercury, and in periods when we plan pregnancy or for pregnant and lactating women and for young children. Smooth-hound shark, sportfish, tuna fillets, and common Pandora consumption of those species should be limited.